Welcome to science class on gravitation for class 9, chapter number 12, CVSE, part 1 of 2. I am K.S. Chandra, PGT Physics, JNV, SENAPATI, Manipur. First, let's try to remember those two pioneering scientists in the field of gravitation, Johannes Kepler and Sir Isaac Newton. First, let's try to see the topics to be covered in our today's video. The first one is gravitational force or gravity, Newton's universal law of gravitation, properties of gravitational force, universal gravitational constant, Kepler's law of planetary motion, Newton's law of gravitation, free fall, acceleration due to gravity, equations of vertical motion, and lastly mass and weight. Gravitational force of the earth, or we simply call it as gravity. You know, a force is necessary to produce motion in a body. The force with which the earth pulls the object toward it is called the gravitational force of the earth or gravity. So we use this word gravity specifically for our own planet, the earth. Okay, otherwise if we mean for other planet, then we don't say like this, gravity of say Jupiter, gravity of Saturn. We do not say like this conventionally. We will say gravitational force of Jupiter, gravitational force of Saturn, like that. But if we say gravity, that specifically mean gravitational force of the earth. The gravitational force between the sun and the earth keeps the earth in uniform circular motion around the sun. Similarly, the gravitational force between the earth and the moon, okay, keeps the moon in the uniform motion around the earth. I mean that moon that revolves around the earth. The gravitational force of the earth or gravity is responsible for different phenomena like holding the atmosphere above the earth, for the rain falling to the earth, and it is also responsible for flow of water in the river, responsible for keeping us firmly on the earth, for the revolution of moon around the earth, as I have said, and for the formation of tides, etc. There are different phenomena, okay, which is responsible for this gravitation, but these are the some of the few important points, okay, responsible for this gravitational force of the earth or gravity. Let's see about the formation of tides. Okay, there are two type of tides, you know it, no? When the sun somewhere here, when the sun, then moon and the earth, when they are along the same straight line, we call it that as tide. So the moon may be somewhere here, sun will be somewhere here, no doubt. Tide may be of that what we call as spring tide, when the sun, moon, earth, the three heavenly body, when these three are along the straight line. So either the moon may be somewhere here or the moon may be here also. Here, if it is moon here, the position of the moon, then moon, earth, sun, like that. So what happen when the moon revolves around the earth like this? What happen? Spring tide may be of two type, okay, in a day. Rather it may be somewhere here when the moon, or when the moon is somewhere here. Got it? And when the three heavenly bodies, sun, moon and the earth, if these three, instead of having along a straight line, rather if they are perpendicular like this, that means when either the moon is at this position or at this position, then we will call it another type of tide known as nip tide. So what happened twice a day, this spring tide or nip tide may happen twice, 2 times a day. Okay, so this is the position of the spring tide, one of the position of the spring tide, and you will see that the water masses of the earth bulges out due to this gravitational pull of the moon. What happened, the water masses that pull toward the what moon, but due to the gravitational force of the earth, rather due to the gravity, again it pulls down again. So there will be what the motion of up and down of this water. Okay, but you will not find this the tides in a small water mass like that of a pond or lake, but you will find these tides in the larger masses of water like that of ocean and sea. And you will not see this tide again in the middle of the sea or in the middle of the ocean, but you will see near the shore where there is what less depth of water. Okay, so what happened, this is about one of the spring tide, and you will see another spring tide here like this. See, in this case this is a spring tide. Okay, the first position of the moon is somewhere here, so all the three are straight line. When the moon is here also, all this sun, earth, moon are along the same straight line, so they are all for a spring tide. And for the nip tide, this is the position of the moon when the moon revolves like this. This is a position of the moon for that of the nip tide. Okay, nip tide, NEAP. Okay, nip tide. Yes. Now for the other position of the nip tide, the moon will be here like this. Got it? This is a nip tide. So the position of these sun, earth, moon, they are along the, not along the straight line, rather they are making 90 degrees somewhere here like that. Got it? So see the water masses bulges or pull toward the moon. Got it? Now let's see about the Newton's universal law of gravitation. I will not go through all the text, rather you try to pause it if you want to note down, and you can copy it very easily. Okay, but I will tell you that this, okay, the important things only. Now this Newton's universal law of gravitation, why it is called universal? Because it is applicable to any object placed in universe, whether it may be on top of the hill, whether it may be in space, whether it may be inside a deep sea. Okay, any two objects having masses m1 and m2. Okay, any two masses, okay, having m1 and m2 and kept at a distance of separation between them with a small r, then what happened, this Newton's universal law of gravitation states that the force of attraction between the two masses, okay, is directly proportional to the product of the masses, so F represents the force of attraction, okay, or the force of gravitation between the two masses is directly proportional to the product of the masses and inversely proportional to the square of the distance of separation between the two masses. Got it? So what happened, this r is the nothing but this is the distance of separation between the two masses, or we take it that distance not from here to here. Okay, we take it the distance as the distance between the center of the two masses. Okay, the centers of the two masses. So from somewhere here to the center of the another mass, this distance is known as distance of separation between the two masses. So collectively we can write it that the force, okay, of attraction between the two masses is directly proportional to m1 and m2, inversely proportional to the square of the distance of separation. So we can collectively write as like this: F is directly proportional to m1 by m2 divided by r square. Got it? Or if we want to change this proportionality into equality, then we require a constant, right? So that constant of proportionality is denoted by capital G. So F will be equal to G times M1 into M2 divided by R square, where G is a constant known as universal constant. Universal gravitational constant. Why we call it this as universal gravitational constant? Because this constant, it will be constant, okay, that will be applicable throughout the universe, okay, as it is your Newton's universal law of gravitation. This law holds, okay, wherever the object is, or wherever the two objects are, I should say. Then what happened, the constant that is coming up there, we call it as universal gravitational constant, okay. And we will come later on how to find it, the value, how to find this unit of this universal gravitational constant. Even though this is a constant, it is a dimensional constant, it has its own unit, okay. Let's see some properties of gravitational force, okay. I mean the properties of gravitational force. Your gravitational force is a weak force in nature, okay. This is the weakest force, I should say. There are four type of forces in nature. The first one, let's take it that this force, gravitational force. The second one is your electromagnetic force. The third one is your nuclear weak force, and the fourth one is the strong nuclear force, or rather we call it that force also as Yukawa force, okay. Now out of these four types of in nature, what happened, the gravitational force is the weakest force. It is an attractive force, okay. There is no repulsive force in the case of gravitation, unlike that of electrostatic or a magnetic force, where when there is a like charges or like poles, they repel each other, okay. But in the case of this gravitational force, it is always attractive in nature, right. It is a mutual force. Means what? When one is attracting, when one mass is attracting the other will also have that attractive force onto the other. So this is a mutual force, okay. When one is attracting the other will also attract the former mass, okay. So this is known as a mutual force, and it is a central force. What is meant by this central force? If that force of attraction, or rather your gravitational force, lie along the line joining their centers, then we call it that type of force as central force. So your gravitational force is also a central force. Next, it is mass and distance dependent. That means your gravitational force is dependent on the masses and the distance, is not it? So what happened, your gravitational force is mass and distance dependent. It depends upon mass as well as on distance. It obeys inverse square law. You see in the equation here, there is a square term in the denominator, okay. So if you want to bring this in the numerator, then it will be r inverse square, right? Inverse means minus. So we call it that type of laws which have this square term in the denominator. We call it that as inverse square. So this is your gravitational law of this universal law of gravitation obeys inverse square law. Inverse square law of what? Inverse square law of distance, okay. It is a long range force. It is a long range force means what? When the object is very far away also, okay. When the object is also at a very far distance, okay, that means the distance between the two masses, if it is very large also, still this gravitational force exists. So we call it that as long range force. That means as distance keep on increasing, what happen, the force between the two masses will still exist, but the value of that gravitational force, or the magnitude of that gravitational force, may be very weak but still exists, unlike that of your electrostatic or magnetic force. When the distance between the two charges or poles, if they are far away, then it will be equal to 0 in that case, right? But in gravitational force, it will not be equal to 0. Got it? Yes, it doesn't depend, the last point I mean, it does not depend on the medium between the two what interacting bodies or interacting mass. If the intervening medium between the two masses, okay, is of water or vacuum or any other else, any medium, it doesn't depend on that intervening medium between the two bodies or between the two masses. So what happened, it depends only on what masses and distance. Got it? So it doesn't depend on the medium between the two what interacting body or masses. That means what, there is no gravitational shielding, okay, unlike that of electrostatic or magnetic force. Now let's see about the universal gravitational constant denoted by capital G. Don't make confused with this capital G and small g, okay. This capital G is universal gravitational constant and its value is equal to what, 6.67 into 10 to the power minus 11 Newton meter square per kg square. Got it? Let me zoom in so that you can see very easily. This is the value of your universal gravitational constant G, 6.67 into 10 to the power minus 11 Newton meter square per kg square. So this is the unit of SI unit of your capital G. Got it? And now let's see, when we come later on in deep into the topic, then we will know how to find out this value as well as how to find out this unit. But for the unit, let me tell you here. Now you see that this is G, okay. Capital G can be expressed as F into R square by M into M, the two masses I mean. So what happened, SI unit of force is Newton, SI unit of distance is meter. So this will be Newton meter square kg into kg square divided by kg square. So from this expression we can easily find out the SI unit of this universal gravitational constant. So its SI unit will be what, Newton meter square per kg square. That is what I have written here, Newton meter square per kg square. So your Newton meter square, distance square means meter square, kg into kg means kg square. So as it is in the denominator, so we have to say per kg square. So Newton meter square per kg square is the SI unit of what, universal gravitational constant. The value of G do not depend on the medium between two bodies, okay. The value of G is same throughout the universe and hence the name universal, right? So universal gravitational constant G is different from acceleration due to gravity, as I said. Therefore correct symbol must be used accordingly, okay. As I told you about this one SI unit, so two bodies of masses 1 kg each are separated by 1 meter from each other, then G will be equal to F. So from this expression, if you take it that these masses of the two body are, say suppose 1 kg each, and if they are separated by a distance of 1 meter, then this will be 1 square, 1 into 1. So this term will be, this factor will be equal to 1, and so your universal gravitational constant will be equal to F, right? So we may define as universal gravitational constant as what, the amount of gravitational force between two masses of 1 kg each separated by a distance of 1 meter, okay. So we may say what, universal gravitational constant G is numerically equal to what, the force of gravitation which exists between the two bodies of unit masses kept at a unit distance of separation, right? Yes, let's go to the next topic and we will see some quick some quick glimpses of your gravitational force. Your gravitational force is the weakest force of all, okay, as I said. So if the two bodies of 1 kg each are separated by 1 meter from each other, then what happened, F is equal to G. That means your G is equal to 6.67 into 10 to the power minus 11. So as it is numerically equal to, that means only numerical value should be taken, the value of G, and your force will be how much? It will be 6.67 into 10 to the power minus 11 Newton. Okay, though the various objects on this earth attract one another constantly, they do not cause any visible motion because the gravitational force of the attraction between them is very small. Why? Because the masses, okay, of the two body under consideration are very small, and as they are also, even though they are very close to each other also, the force may be very weak and it may not be recognized or realized. Okay, imagine a situation on the earth if the objects continuously move toward each other due to the gravitational force between them. Now when the objects are very big, okay, when the objects are very big, having very large masses, then gravitational force of attraction between them becomes extremely large. If that is extremely large, then we may realize it. Okay, suppose the gravitational force due to the earth on an object of mass 1 kg placed on the ground, it will be equal to 9.8 Newton. So this is very weak one. Okay, this is very weak. 9.8 Newton is not that much small as when we consider about the gravitational force between the earth and the moon. Even though they are at a very far distance also, what happened, their gravitational force comes out to be 2 into 10 to the power 20 Newton. Okay, so this is very large. So when the objects are very large, then only we can realize it. You may not feel even the force of attraction between you and your friends sitting in the class, no? Why? Because your mass and your friend's mass, the two masses are very small. Even though if you are very closely seated in a classroom, what happens, you will not feel or realize or recognize any force of attraction of your friend toward you, or your friend will not recognize the attraction of you toward him. Okay, let's see about the ellipse. Before going to that law of what Kepler's law, I mean Kepler's planetary law, let's try to see about the properties of ellipse first. Now in the case of ellipse, okay, this is an ellipse, not a circular one, rather this is an ellipse. Okay, in the case of ellipse, what happened, if you try to join any 2 points, okay, on the ellipse like this, any 2 point, and if that line joining any 2 point, if it is the longest, then that line will be like this here, passing through these 2 points. Okay, and that line we call it as what, major axis. So onto this major axis there are 2 points which is known as foci. In plural we call it foci, in singular we call it as focus. So there are 2 focus, okay, 2 focuses we have to say, or rather you can call it foci, okay, in plural. So what happened, these 2 foci, okay, if you try to take these 2 lines joining, okay, what happened, this focus and this point, then what happened, the line joining these 2 foci and what happened, this point, what happened, this red line, you will see the foci and this particular point on the ellipse. Okay, this line plus the line joining the other focus and this point, what happened, the sum of these two will remain constant. Wherever it is, somewhere here also that line will remain constant. You will see in the picture there. Okay, this is a constant. So the length of these, what, if you take it a thread like this, the length, the red thread represents, this red line represents, that's just like a thread, and if you make it like this, then it will be an ellipse. Okay, but if you join a tangent, okay, about this, suppose if you join a tangent at this point like this onto this ellipse, then what happened, the angle formed between the tangent and this line joining this particular point on the ellipse and the focus, then what happened, this angle that is formed there, it will remain constant. Okay, it will remain same. I mean, suppose if you draw a tangent somewhere here on this, say if you draw a tangent here for example, then the angle between this tangent and the line joining this point and this focus, this angle, it will be having the same value. here also theta, and here also it will be theta. Got it? So this is about the property of the what ellipse. And if you join it here, then this will be known as what? If you join it this, then let me take you first again to this like this. If you join it this line, okay, passing through these 2 points, then this line we call it as what? Major axis. And at the middle point of this point, if you draw a perpendicular line like this, then this line which is drawn perpendicular to the major axis, we call it as what? Minor axis. And this minor axis will be the what? Perpendicular line drawn at the major axis at its midpoint. Okay, this is about that of an ellipse. And when we go through that Kepler's law of planetary motion, we will come all these things. That is why I am just saying about this, okay, about the ellipse. Okay, let's try to go to that of what? Your planetary motion. And that law governing this planetary motion, we call it that as Kepler's law of planetary motion. And there are 3 laws. The first one is law of orbit, the second one is known as law of area, the third one is known as law of time period. So let's see first, okay, for the first law of orbit. Now this law of orbit, or rather your Kepler's first law of planetary motion, states that all planets revolve round the sun, okay, in an elliptical orbit with the sun at one of its focus. Got it? So what happened in that ellipse? Okay, in that major axis there will be 2 points. Okay, out of these 2 points, one will be the focus will be the position of the sun, and the planet will revolve in that particular ellipse. Suppose if there is another suppose if there is another ellipse like this, somewhere here like this. Okay, let me draw it somewhere here like this in a different plane. Okay, and if this is its major axis, got it, then what happened? One focus will be somewhere here, another focus will be somewhere here, and one of the focus will be surely the position of the sun, and this ellipse will be the orbit of that particular planet. Got it? Another may have like this somewhere here in the plane, in the different plane. Okay, it may not be just like this, but it will be having different plane. That is the meaning. But in lower class you might have seen that all planets are drawn like this with the sun at the center like this. This is the sun, and all the planet Mercury, Venus, Earth, Mars, we draw it like that in the lower class. Okay, in the same plane, but it should not be in the lying in on the same plane. Okay, that is a wrong concept. So what happened? The plane of this ellipse for those orbits of the planet, it will be at different what? Planes. Okay, got it? Yes. So let's continue. Now I'm just drawing for different planets, but it is not seen very clearly. So let's concentrate it on our Earth, the planet Earth only. And this green ellipse represents the ellipse, the elliptical orbit of the Earth. Okay, and this sun will be at one of the foci of this elliptical orbit. Got it? So that is the first law. The first law states that all planets, okay, revolves or moves around the sun with the sun at one of the foci of the elliptical orbit. Got it? And the next one is what? Law of what? Area. So before knowing that law of area, let's go to this elliptical orbit of the Earth first. Okay, now this is the position of the sun, and one focus may be somewhere here. Okay, so what happened? This distance, suppose see it is the of 147 million kilometer, and the distance between the sun and somewhere here on the other part of the major axis I mean the other part of the ellipse on the major axis, it will be around 152 million kilometers. So there is a difference here. No? This one is shorter and this one is longer, right? So what happened when the earth revolves around such an elliptical orbit? What happened? There will be a closer distance, the closest distance somewhere here, and the farthest distance somewhere here between the sun and the planet. I mean that particular point where there is the nearest point, we call it as perigee. Okay, perigee is the point where it is the shortest distance between the sun and the planet, and the longest distance that between the sun and the planet, that particular point on the elliptical orbit, we call it as apogee. Got it? So what happened as this earth, let's take it for our earth, this earth or the planet earth revolves around the sun in this elliptical orbit, gives you the different seasons, okay, or rather the different month. So when somewhere here at what perigee, what happened, you will have that of the winter season. Okay, don't think that when the planet is closest to the sun it will be the hottest. Okay, generally students think like that. Okay, but it is not so. Why it is so? Because your axis of rotation of the earth is tilting. It is not with the vertical to the plane, but it is tilting with the plane. Okay, an angle of 23.5 degree from the vertical axis. Okay, vertical means vertical to the plane of this axis, right? So what happened, vertical to the plane of this elliptical orbit, I mean. So there is an what tilting of this axis of the rotation of the earth. So due to that, what happened, even though this planet is somewhere here closest to the sun's ray are not falling normally onto the surface of the earth, rather they are falling what slanting. You may experience every day like that, when in the time at the time of sunrise and at the time of sunset, you will not feel that much hotness, okay, as in the case of noon. In the case of noon time, what happened during the noon time, the sun's rays falls on our overhead. Okay, on our overhead, that means the sun ray is perpendicular, okay, to the surface, whereas at the time of what sunrise and sunset, the sun's rays are not falling perpendicular to our earth surface, so we do not feel that much hotness. Same is the case here also. What happened, even though it is closest here, what happened, the sun ray are not falling what perpendicular to the surface, so we call it that position of the sun somewhere here, that will have that winter season. So winter, spring, summer, autumn, then again winter again. So like that we will have it different seasons. Okay, now let's go it to the different positions. Now in the case of somewhere here in January, it will be what that near the perigee, and in that of June and July, somewhere there it will be what your apogee. Okay, let's see. After knowing this, then we will go to that of the second law, known as law of area. Okay, law of area states that, that means your Kepler second law states that the time, okay, if you take it a time, particular time interval, got it, say time interval, let's take it somewhere here from say December. Okay, December 1, you take it a time of from December 1 and it comes here to December 31st. Let's take it as an example. So what is the time? It is time for 31 days, and let's take it that as a 1 month. Okay, so during the time of 1 month, the planet which was here will now come slowly like this, and if it reaches at this position D, so to move the planet from the position C to D onto this elliptical orbit, it takes 1 month. So your time is how much? 1 month. How many days? 31 days. Let's take it, okay, as an example. So the time taken by the planet to move from somewhere here to here, let's take it that time as what? 31 days. So somewhere other than this, let's take it somewhere here from the point A to point B. during this time of say 31 days, let's take it from January 1st January, okay, to 31st January. When the planet was at position A, it was 1st January. So the time taken by the planet from A to reach to this point B, it takes again 31 days. Got it? So during this same time interval, okay, during this same time interval, the area swept by the planet, okay, the area, okay, swept by the line joining this sun and the planet, this line, so it will be CS in my case here, okay, the line joining the planet and the sun sweeps equal area in equal interval of time. That is the statement, okay. The area swept by this line joining the planet and the sun, that area will be this shaded area. Am I right? In that period of what, 31 days. So you take it another 31 days somewhere here also, and the area swept by this planet and the sun, that line, okay, joining the sun and the planet sweeps what, the same area that is swept by that line joining the sun and the planet at some part of the what, orbit. Suppose if you take it somewhere here, okay, in around that of say, suppose let's take it as around Mars, okay, Mars, and it is suppose somewhere here it is coming as what, April somewhere here. Then the line joining this, okay, planet and this sun, it will take say the line joining this, that will be this line. So the area swept by this line joining this planet and the sun, that area will be this area. Am I right? So this area will remain same. Okay, suppose if it is little bit it should be little bit longer like this, so that it will have the same area. Okay, so this time, okay, this will be also what, 31 days, right? 31 days. So during the same, okay, time, what happened, the line joining, okay, this planet and the sun will sweep equal area, okay, that is known as what, your law of area. Again, let's state it that the law of area states that the line joining the planet and the sun sweeps equal area in equal interval of time, okay, that is known as what, law of area. Now from this law, what we can conclude is that when the sun, okay, is at one of the focus and the planets revolve in its elliptical orbit, the speed of this planet, okay, when moves around the sun, it doesn't have the same speed, okay, it doesn't move with a constant speed. Rather, when it is coming closer, okay, when it is coming closer toward the sun, it speeds up, and when it moves far away from the sun, it slows down like this, okay. It will be increasing its speed and it will be slowing down like this. Got it? It will be slowing down. When it comes toward the sun, it speeds up in this portion, in this way. Got it? So let's see for the next one. That is what, law of what, time period. Now I will tell you about a time period first. What is this time period? The time period is nothing but the time taken by the planet to revolve once around the sun. That time we call it as time period, and it is denoted by capital T. Okay, the time taken by the planet to revolve once. Suppose if you started from this perigee, okay, and if it goes like this and if it comes again, the time taken, that will be what, it will be 1 year, right? Okay, that will be 1 year. That 1 year we call it as time period, and it will be denoted by what, capital T. Got it? That will be denoted by capital T. Now that time, why? Because it is a time taken by the planet to revolve around the sun once. Got it? And now the most important one again, that will be coming up in this third law of planetary motion, or rather we call it as law of time period or law of period simply. what happened? The distance between the sun and the planet, okay, this will keep on changing. This will keep on changing, right? Longer, 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 okay, and this will be the longest, and it will become decrease, decrease, decrease like that, no? So that means the distance between the sun and the planet, it keeps on changing. So if you take it out, the average of all these, okay, distances between the planet and the sun, okay, for one complete revolution, that distance between the sun and the planet, we call it simply as mean distance, okay, between the planet and the sun, or mean distance you can call it, or average distance between the sun and the planet. Got it? It will be greater than the shortest distance, it will be smaller than the longest also. It is the mean or average of all those different distances between the sun and the planet. Got it? So let's go to the next one, that is nothing but law of period. So this law of period or law of time period states that the square of the time period of revolution of the planet around the sun is directly proportional to the cube of the mean distance between the sun and the planet. So this is the mathematical expression, okay? So your law of time period, or Kepler's third law of planetary motion, states that the square of a time period is directly proportional to the cube of the average distance between the sun and the planet. Or if you want to write it in equation, then this proportionality symbol need to change into equality, then we will require a constant, okay? So we can express also as what t square by r cube is equal to constant, okay? This will give you what is known as what law of period or law of time period. Though Kepler gave the law of planetary motion, he could not give a theory to explain the motion of the planets, okay? Only when Newton explained the cause of motion of the planet, okay, is the gravitational force which the sun exerts on them. So only when Newton explained that this rotation of all the planets, revolution of all the planet around the sun, it is nothing but it is due to the gravitational pull of this planet on toward the sun, okay? That was the Newton's explanations about the planetary motions. Newton used Kepler's third law, okay, this law, to develop the law of universal gravitation, okay, the law of universal gravitation. Got it? Yes. Now let's see, according to Newton's third law and universal law of gravitation, every object attracts every other objects with a gravitational force, that we know it, okay? These forces are equal and opposite. When one is acting, okay, onto the other, that force will be also equal to the force acted upon it by the other, okay? So what happened, these two forces are what, mutual forces. But what happened, therefore both the object must be moving toward each other due to the force as they are attracting, okay? However, due to very weak nature of the force, the normal sized body are not seen moving toward each other, okay? As the masses of the two objects are small, we will not see that they are moving toward each other. What happens, a ball is dropped from a certain height from the ground, you will see that ball is falling toward the earth, but you will never see that your earth is moving or flying toward the ball. You will not see, rather you will see the falling of the ball on toward the earth. Why it is so? Now I will give you the reason here. Let's take it the mass of the ball as small m, okay, and the mass of the earth as capital M. Why? Because capital means large, right? So this, let's take it the mass of the earth as what, capital M, and the mass of that light ball, you take it small m. So the force experienced by the ball, okay, due to the gravitational force of the earth, that will be, as it is a mutual, that will be same. The force experienced by the ball due to the earth, that is also capital F, the gravitational force between the ball and the earth, the force that is experienced by the what earth due to the gravitational force of the ball, that will be also this capital F. Okay, and let's take it that by Newton's second law, F is equal to mass into acceleration. From it you can find out acceleration of the ball, acceleration of the earth. So as this F is constant divided by small m, so naturally your capital A will be less. Okay, let's see, let me show you. Okay, now this A, what happened, you take it that capital F as 100 divided by 2, and on this side you take it that the same force as 100. This is a numerical example. Okay, this is not the actual value. Okay, now if you take it divided by this 100 divided by a bigger quantity, then this will be equal to 2, right? But if you divide that same force by a lighter mass, let's take it that lighter mass, it will be equal to what, 50, right? So if you divide by a smaller quantity, the quotient will be large. If you divide by a bigger quantity, then the quotient will be small. So what happened, the between that force of attraction between the ball and the earth, you will see the motion of that of the lighter mass. Okay, because its acceleration is more than that of the bigger mass. Got it? So you will not see the motion of the earth on toward the ball, rather you will see what, the larger acceleration, that is the motion of the ball toward the earth. Got it? Let's see in the next slide. Yes, about that of free fall. What is this free fall? Now if any object falls, okay, from a certain height onto the earth without any external force except that force of gravity, then that type of falling we call it as free fall. Got it? So free fall is a phenomenon, okay, of that of falling of an object from a certain height freely without any external force except the force of gravity, then that phenomenon is known as free fall. And the object that is experiencing the free fall, we call it as free falling object or free falling body. Galileo proved that the acceleration of an object falling freely toward the earth doesn't depend upon the mass of the object. So for that to prove, the Galileo had already proved that experiment, okay, in that leaning tower of Pisa. Okay, now we can also do it in the same way also. You can take it a cylindrical jar of which the two ends can be fixed or covered. Okay, and you can evacuate the gases present there, okay, by using a vacuum pump. And if you allow to fall down a light feeder, okay, and a heavy coin at the same time simultaneously, I mean, then the two objects, feeder as well as also coin, will reach the bottom simultaneously. Okay, the time taken by this feeder and the coil to reach the bottom surface, it will have the same time, it will take the same time. That means the acceleration due to gravity of these two masses, okay, is constant, same. That means your acceleration due to gravity, okay, these objects are falling downward due to the gravity. Okay, so we call it that rate of change of velocity of this falling object, we call it as what, acceleration due to gravity. So your acceleration due to gravity is independent of the mass. That shows what this is the nature of or the property of free falling object. Okay, it will have the same acceleration, and this shows that your acceleration of the free falling object doesn't depend upon the mass. Okay, if this is light mass, heavy mass, if they both reaches at the same distance at the same time, that means what, the acceleration of these two objects, I mean the acceleration of falling, is independent of the mass. Got it? Yes, let's see about the acceleration due to gravity. Okay, what is this acceleration due to gravity? I will go to that one again first. Now as these objects, okay, falls toward the earth, that means it keeps on, okay, moving toward the surface of the earth. Why this object is moving toward the earth? Because the gravitational force of the earth, rather the gravity, okay, it pulls, okay, the gravitational force or the gravity pull this object toward the center of the earth. So we know that your center of the earth, I mean the distance will be what? Your distance, say, as it is expressed as what? F is equal to G m1 m2, I will use it as a capital 1, okay, divided by distance square. Now this distance keep on decreasing as it falls toward the surface of the earth, right? As it falls toward the surface of the earth, okay, this distance keep on decreasing. So as distance decreases, what happen? The denominator decreases, that means force will be increasing. So as this object, falling object, comes nearer and nearer to the surface of the earth, the gravity or the gravitational force, okay, on experience onto this mass, this will keep on increasing. And so what happened? The pulling force will be more and more as it come closer and closer toward the surface of the earth, right? So what happened? The velocity of this falling object will keep on increasing, okay? So what happened? The rate of change of velocity, as the velocity increases, what happened? The rate of change of velocity, that means change of velocity of this falling object per unit time, what? That will be having a constant value, okay? I'm not saying that velocity is constant, but the rate of change of velocity is constant, and that rate of change of velocity, we call it as acceleration, and it is due to the acceleration, due to the gravity, so we call it that acceleration due to gravity as acceleration due to gravity simply. Got it? Now let's see how to find out that value, and that value I will give you here, and I will try to find out here by using this formula, and the value is what? 9.8 meter per second square if it is onto the surface of the earth and near the surface of the earth, okay? If it is little bit above the surface of the earth, also it will have this value 9.8 meter per second square. Here the symbol used is small g. It is different from that of the universal gravitational constant capital G, okay? And this is also what? A dimensional constant. It has unit meter per second square. In CGS unit it will be 980 centimeter per second square, okay? So how to find out the value of this acceleration due to gravity? When that object is falling, okay, that is a gravitational force. That gravitational force is nothing but the weight, okay, of that particular body. Suppose if you place an object here like this onto the surface, then this object is experiencing the gravitational pull of the earth, okay? That gravitational force is nothing but the weight on experienced by this mass m, that will be equal to mg, right? This weight is nothing but the gravitational force, okay? So then these two forces are equal. Then if we equate these two, then what happened? This m and m, small m and small m will cancel, okay? Small m is the mass of the object, capital M is the mass of the earth, and as the object is placed above the surface of the earth, distance between the two objects will be treated as the radius of the earth, okay? As it is a small mass, the radius of this small spherical mass will be very negligible, and it can be taken as simply as capital R as the distance between the two objects, earth and the object, okay? We will not take it that distance as 0, as I told you that in the case of that universal law of gravitation, what happened? The distance between the two objects means the distance between their centers, okay? So your radius of the earth will be the distance between the two objects, capital M and small m. So after cancelling m, your g can be expressed as what? Capital G m by r square, where g is a universal gravitational constant, m is the mass of the earth, r is a radius of the earth. So g will be equal to gm by r square. Remember it to use this as the formula for acceleration due to gravity. So when you put this value of what? Capital G, that is your universal gravitational constant, 6.67 into 10 to the power minus 11, and that of the radius of the earth as 6.4 4 into 10 to the power 6, or rather you can call it as 6,400 kilometer, okay, and mass of the earth as 6 into 10 to the power 24 kg. Then if you calculate it by putting those values here, then you will get it as 9.8, okay. And this is acceleration, so it will have the SI unit of acceleration, meter per second square, okay. For simplified calculation, we can take what your g as 9.8 means approximately as 10. For sake of simplicity, you can take it g as 10. Okay, in the calculation of any of these related to gravitation, if not stated, okay, you should not take that g as 10. Rather, you should take as 9.8. Okay. Now this acceleration due to gravity, okay, varies its value depending upon various factors. Let's see some quick look onto these different factors, okay, on which this acceleration due to gravity depends. Now acceleration due to gravity decreases with altitude. If you keep on increasing the position of this object small m, okay, above the surface of the earth, then what happen? Your distance between the earth and that object r will be replaced by what? R plus height. Got it? If your object is somewhere here, then we can't take it that distance between this object of mass m and this. You can't take it as radius. Rather, you have to take it r plus height will be the distance between that object somewhere here of mass m, I mean, and the center of the earth. So what happens if this denominator increases, then the whole quotient decreases, right? So your acceleration due to gravity decreases as what happened with the altitude. Got it? So higher the altitude, lesser will be the acceleration due to gravity. So maximum is somewhere here, and then what happened? It keeps on decreasing, and when it is at infinite distance, rather at infinity, you can say your acceleration due to gravity will be equal to 0. Okay, let's see some other factors also. Acceleration due to gravity decreases with depth. When you go down, okay, toward the center of the earth, suppose hypothetically we have to say like that, if you, but no one can enter inside the center of the earth, it is very hot, okay, but hypothetically we have to take it theoretically, okay. When you take it somewhere here at this depth, then what happened? Instead of having plus heights here, it will be minus. Got it? So in class 11 you will learn how to find out this expression, okay. You have to take, suppose if it is at this point, then you have to take only the mass of the earth as this much only, this much portion, okay, not the whole one. So due to that, what happened? Your formula here comes out to be r minus heights, okay. But still there is a square term is there. So what happened when you move down, okay, deep inside the earth, acceleration due to gravity decreases, okay, and its value, acceleration due to gravity at the center of the earth, will be equal to 0. So what happened? The maximum value of acceleration due to gravity of the earth is on its surface. When you go higher and higher, it decreases. Acceleration due to gravity small g decreases. When you go deep inside, okay, more and more, deeper and deeper, acceleration due to gravity decreases, and it will be 0 here at the center and also at infinity, okay. And now acceleration due to gravity is greater at the pole and less in the equator. Now around 21 kilometer, okay, the difference between the radius, okay, of the pole, I mean radius of the earth at the pole and at the equator. Your earth is a flat oblate, okay, it is not a spherical. The radius are not constant. Onto the equator, it is somewhat longer than that of the radius of the earth onto the poles, okay. So what happened? The difference between this distance is around 21 kilometer. So your RE, that means radius of the earth at equator, radius of the earth at poles, denoted by RP. So your RP is less than RE. Got it? And so what happened if you try to find out your acceleration due to gravity at poles and equator like this, then what happened? This RP is less, RE is more, okay. So what happened? More the denominator, lesser will be the quotient. So your acceleration due to gravity at equator is less than that of the acceleration due to gravity at poles, okay. So this is also due to the fact that your earth is not a spherical surface. Got it? Yes, like that. no, if you want to know the actual values, then you can have it here like this. So acceleration due to gravity, okay, on the poles or at the poles will be around 9.823 meter per second square. Acceleration due to gravity at that of the what equator will be 9.789. So see, there is a difference, okay, and we may take it that average value as what 9.8 meter per second square. Okay, whatever we are having, that acceleration due to gravity 9.8 is the average value, right? Let's see about that of the equation of motion. This is very important, okay, when you try to solve the numerical problems relating to this free fall, okay, or of a falling object. Let a body be thrown vertically downward. Okay, you are suppose standing on a terrace like that, and if you throw a stone downward, that is the condition. Okay, let a body be thrown vertically downward with initial velocity u. Okay, let the final velocity of the body after time t be denoted by small v. Let h be the height of the vertical distance covered by the body, and small g is the acceleration due to gravity. Then we will use, while at the time of this falling or throwing upward, okay, we will use those kinematic equations that we use in the case of linear motion. But the only difference is that what happened, your acceleration will be denoted by acceleration due to gravity. Your distance covered or moved by the body will be replaced by the height. That much difference, okay. Others are almost same. So you have to take this what sign convention when the object is falling, okay, downward. Then what happened, you have to take it that that's the sign convention: initial velocity, final velocity, acceleration due to gravity, height. This will be all taken as minus. Got it? You have to remember this, okay? Initial velocity, final velocity, acceleration due to gravity, height. This will be all need to be taken as negative, but you can't take it time negative, okay? So what happened? Except this time, others are all negative. All those physical parameters you can say: initial velocity, final velocity, acceleration due to gravity. So if you take it all those as a negative, then you will get it the expression v minus u is equal to at. Got it? That is the expression. Or you can take it that expression as what a is equal to v minus t, v minus u divided by t. We have the expression that a is nothing but this is the rate means in the denominator it is time, right? Change in velocity, rate of change in velocity. Change in velocity is what? V minus u. V is what? Final velocity. U is what? Initial velocity. So if you want to find out change in velocity, then it will be v minus u. And the time taken to change this velocity, if it takes small t, then if you divide this change in velocity by time, then we simply say that rate, the word rate is used. So rate of change of velocity, we call it that as acceleration, right? So your acceleration due to gravity here, it will be denoted by small g, not by small a, okay? This is just your small g. So this will be denoted by what? Small g. Got it? This is denoted by small g. So what happened if you take it that expression, then it will be, this will be equal to v minus u is equal to at. So in this first expression or equation, it expressed as v is equal to, if you transfer this to that right side, then it will be u plus, instead of a, it will be now g, right? So it will be gt like this. So if you use this as minus u, got it, here as minus u minus g, minus u, I mean minus v minus u minus g, then what happen if you cancel it all those minus, then you will get it this first expression. Got it? In the same way, if you do that of for this, the second equation here, this is the second equation, then what happened? Your s is equal to ut plus half at square, right? So instead of s, you have to write as h, instead of u, that will be u there, no doubt, plus half. Instead of a, you need to use g, acceleration due to gravity, time as t square, like this. That is what it is here in this second equation. Similarly, the other also you can do it, that v square minus u square, this is equal to what? Twice as, like that, no? In the case of linear motion. So instead you have to write like this, v square minus u square, as it is like this, equal to twice. Instead of a, you have to replace it by g. Got it? And instead of distance, you need to replace it by height. So that is what that is having in this third equation. Got it? So similarly, you can find it out for others also. Okay, those three kinematic equations can still be used, but only the sign convention you need to do it in this way. So at the time of during the case of falling of an object vertically downward, okay, on toward the ground, then what happened? You need to take it this sign convention in order to use here in these kinematic equations. So for the next one, let's see. For the next one, what happened when a body is dropped freely? Okay, in this case it may be throwing downward, but in this case it is a free fall. Okay, so there will not be no external force except the force of gravity. Then what happened? Before falling, what happened? The object was at your hand, so that means its initial velocity is 0. You have to take it this one. Okay, the others will remain same, minus v minus z h. Okay, this will be all taken as minus, similar to that one. Okay, if you put u equal to 0 in the above equation, then you will get like this. The last one, when a body is thrown vertically upward, okay, when the object is thrown vertically upward, in that case what happened? U, v, h, this will be all positive except that acceleration due to gravity. Your acceleration due to gravity is falling downward like this. Okay, and at that time what happened? This body is moving against that gravity, so we have to take it that minus z only here. Others are all positive. Okay, all the physical parameters except acceleration due to gravity are positive. This acceleration due to gravity is negative, so you put it that minus g minus z minus z here, then this term will be only minus. Okay, the other will be remaining same. So you have to use this sign convention, or rather the sign to be taken while calculating your problems related with that of your gravitation, okay, of falling, okay, or of motion of vertically upward direction. So those are the things that I have given here about that, and this description is about that sign convention only. Okay, what to be taken plus, what to be taken minus. Okay, that one you can pause it and you can read it. Okay, so let's go to the next one, that is about the mass. Okay, let's go to the learn about mass and weight. Okay, let's see what is this mass. Mass is nothing but the amount of the matter present in a body. We call it that as mass. So we measure mass by using what? By this balance. Okay, it may be physical balance, it may be of beam balance, or it may be by using what? Spring balance also. Now if you want to measure the object, then you have to put it that object onto one side of the pen, and you have to give that standard mass onto the other side of the pen. Now in my diagram here, it is of what this is of what 50 gram plus 10 gram. That means the mass of this object is what? 60 gram. Okay, 60 gram. So if these two, okay, are of same mass, then this physical balance will be in the equilibrium position. They are balanced. Okay, if this is light than this one, then this will be heavier, so it will pull more downward than this. We are measuring the mass, rather actually this mass is experiencing a gravitational force toward the center of the earth. The same thing, this is also having the gravitational pull toward the center of the earth. So the two forces, okay, acted here onto this different mass. If they are equal, then we can compare the mass of this object with this one. Okay, then what happened? We can easily find out the mass. So if it is 60 here, then this will be also of 60 gram. The mass of this object will be of 60 gram. Now let's see about the properties of mass. The definition, as I told you, this is the amount of the matter present or content in a body. Okay, mass of a body is measured of inertia of the body and hence called inertial mass. Now inertia, it is a, we have learned in the case of Newton's law of motion that of inertia. Okay, inertia is nothing but it is the inability to move or to change its position or to change its state by itself without any external force, right? So what happened, larger the mass of the body, what more will be the inertia, more will be the inability to change its state. Okay, so what happened, mass is a scalar quantity, its SI unit will be kilogram, no doubt. In CGS it will be gram. Mass of the body is a constant and does not change from place to place. Wherever it goes, the mass of that, okay, body, the matter present in that body will remain same. When it moves very fast also, mass will remain same. Okay, but in higher classes, when it moves with a velocity comparable to that velocity of the light, then mass can be increased. That one is a different one. Now whatever we are learning is of that of non-relativistic mass. Okay, you will learn the different thing in higher classes, but up to your standard, let's take it that mass is what, constant quantity, and it doesn't depend on places, it doesn't depend on what, any other parameter. The matter present in it will remain same. So it can be measured what, by a beam balance or a common balance. Okay, that common balance means that I have shown you just in the previous slide. Okay, mass of the body can never be equal to 0, but this will be all different in the case of weight. Okay, mass can never be a 0 quantity. Mass is a scalar quantity. It is independent of any of the positions of that mass. Okay, wherever it is, mass of the body will remain constant. Okay, now let's see about the weight. Weight can be measured by using a spring balance, and that weight by spring balance or common balance it can be. Okay, if you find out mass, then mass into acceleration due to gravity at that point will give you that weight, no doubt. Okay, so here I measure it and it comes out to be around, say suppose 60. Okay, so 60 gram weight. So 60 gram weight means 60 gram into acceleration due to gravity at that point, that is 980 centimeter per second square. So if you multiply these two, okay, then you will get it as 58,800 dynes. Dyne is the CGS unit of what, force. Weight and force has the same unit. Okay, or you can express it in terms of Newton also. Okay, so like that, if you put it that value, then you can find it out the SI unit. Okay, if you are going to measure in terms of this gram weight is the unit for weight, don't forget it. Okay, or kg weight. Okay, if it is of mass of kg, express this mass in kg, then you have to say kg weight. In that case, what happens, you need to multiply by your acceleration due to gravity in SI unit. That means if suppose if it is 60 kg, then you have to multiply it by 9.8. Okay, not by 980. 980 for it is for the CGS unit. Okay, if it is only when it is gram weight, then you have to multiply it by 980. If it is of kg weight, then you have to multiply it by 9.8. Okay, so what is this weight? The weight of a body on the earth is nothing but it is the force of attraction with which that object is attracted toward the center of the earth. So your weight is nothing but this is the gravitational force, okay, experienced by that object with respect to that earth in the case of our planet. Okay, that means weight is the gravitational force experienced by that object pulling toward the center of the earth. Okay, so weight is equal to what, mass into acceleration due to gravity. As I said, the SI unit of weight is Newton. Weight of 1 kg, mass is 9.8 Newton. Why? Because if it is 1 kg, acceleration due to gravity is 9.8, so it will be 9.8 Newton. 1 into 9.8, right? Weight is a vector quantity. Why it is a vector quantity? It will be acted in a particular direction. In what direction? Toward the center of the earth. It has magnitude as well as direction. Okay, magnitude will be what, of any numerical value, and the direction will be always acting vertically toward the center of the earth. So it has a direction. It has magnitude as well as direction, so it is a vector quantity, right? Weight changes from place to place. As this acceleration due to gravity changes from place to place, what happens? Your weight will also changes from place to place, right? At a high infinity, Okay, at infinite distance, infinite height, your acceleration due to gravity will be 0. So there the weight of the object will be equal to 0. We call it that. At that point where weight is equal to 0, we call it that as weightless. Got it? That is what is experiencing by your astronauts when they are flying at a very high altitude, high above the earth. Okay, they seems to be floating. Why? Because there is no gravitational force acted onto them, right? Yes. Now weight is measured by a spring balance, as we have seen in the previous slide. Weight of a body can be equal to 0, as I said. Okay, when the body is taken to that center of the earth or at that to that of the height, what happen where there is acceleration is equal to 0, then what happen, weight of the body will be equal to 0. On the moon, what happened, your acceleration due to gravity on the earth, when you compare with that acceleration due to that of the moon, acceleration due to that of the moon, then what happened, your g, okay, small g varies by about 6 factors. Okay, by a factor of about 6. So what happened, acceleration due to gravity onto the earth, okay, this will be acceleration due to gravity onto the earth, this will be equal to 1 by 6 times that of say, no, I'm sorry, it should be 6 times of that of let me, okay, let me do it here. So what happened, your acceleration due to gravity onto the earth, this will be equal to 6 times that of the acceleration due to gravity on the moon. Okay, so this is onto the moon, right? So what happened, your acceleration due to gravity on the earth is greater than that of the acceleration due to gravity on to that of moon. Got it? So how much it is more? By a factor of 6. So whatever you measure yourself around say 60 kg here onto the earth, the mass, okay, or you can say kg weight, you will measure your weight there onto the moon simply as what, 10 kg there, 10 kg weight you can say onto the surface of the moon. So there is a difference of a factor of what, about 6, right? So with that, we come to the end of our today's topic, and we will try to discuss the remaining portion of this lesson, okay, on to that second part of 2. Okay, with that note, let me conclude it here. Thank you.